Okay, so we're going to move on from those basic ideas of redox and start looking at oxidation states and oxidation numbers. Essentially what this means is we're going to use a tool to help us work out when oxidation and reduction are occurring if electron transfer isn't clear. So generally what this means is if we're dealing with covalent compounds rather than ionic. So it's clear with ionic, not so clear with covalent. So let's get going. The main things we want to be able to do after we have completed this video and taken our notes is be able to determine the oxidation state or the oxidation number of metals and non-metal elements in both ionic and non-ionic compounds, so covalent compounds, which means we can follow the rules for the calculation of oxidation states for elements that have variable oxidation states, okay, and this is pretty much anything that we don't have a rule for, which we will look at. Use the changes in oxidation states of elements to determine if a reaction is a redox reaction or not. And then understand that an increase in oxidation number means that an oxidation reaction has occurred, and conversely, a decrease in oxidation number indicates reduction. So let's get started. The reason we need to use oxidation numbers or look at oxidation states, and I'll use those terms interchangeably, is because sometimes with a redox reaction, our transfer of electrons is not very clear. We know that when we looked at the reaction for magnesium solid plus oxygen gas forming magnesium oxide, this one's pretty clear as to what's happening with our electrons because we go from magnesium solid, which has no charge, to an ionic compound that we know is made up of Mg2 plus ions and O2 minus oxide ions. So we can see when we form an ionic compound by definition that we have a transfer of electrons and this is a redox reaction. The case with combustion reactions and reactions that involve covalent compounds is not as clear. In this complete combustion reaction, okay, we can't see if we're forming ions. The transfer of electrons isn't complete. It doesn't form ions, so we can't see what's going on. And this is because the electrons are shared. They're changing the way they're being shared, though, when they change the molecules. So the type of bonding alters this. Because the bond is polar, we know that electrons spend more time with oxygen atoms, so the transfer of electrons from the carbon is only partial. And in this case, we need a way to be able to determine if oxidation or reduction has occurred. And this is where oxidation numbers come in. So when we look at oxidation numbers, these are things that we can be used to decide if a redox reaction has occurred. Okay, they're defined to enable reactions involving molecules to be classified as redox or not. It's important to realize that these have no physical meaning. They sometimes relate to the charge, but not always. So oxidation numbers themselves are an imaginary number. They're a tool that we use. They don't relate to something physical about the compound itself. And then we have a set of rules that we use in order to determine these. The reason we like to use oxidation numbers is because it's one of the only times that the term oxidation and reduction tend to make sense. If our oxidation number increases, okay, so say in the case of magnesium, we'll use this as an example, solid going to magnesium 2 plus. The oxidation number here on magnesium solid is 0. The oxidation number here on magnesium is plus 2. So we can see that going from 0 to plus 2, the oxidation number has increased. And by definition, that means oxidation has occurred. If the oxidation number decreases, then reduction has occurred. So it's a really handy way for us to be able to identify our redox pairs in a reaction. So if we have a look at this, anything that is in elemental state, so H2 gas, N2 gas, O2, anything that is in its natural elemental state will have an oxidation number of 0. So here, H2 has an oxidation number of 0, O2 has an oxidation number of 0. When these two elements react, we get water. And if we have a look at this, we can see that this is actually a redox reaction because the oxidation number on hydrogen in a molecule is +1. And the oxidation number for oxygen in a molecule is -2. So we can see that hydrogen went from 0 to +1. so it has been oxidized, and oxygen has gone from 0 to -2. So it's gone down, and we can say that the oxygen was reduced. Okay, so in this case, because we have an oxidation reaction and a reduction half equation, we can state that this was a redox reaction. Okay, so the formation of water from hydrogen and oxygen is actually a redox reaction. The rules for dealing with oxidation numbers, you need to memorize them. Okay, sorry, you just do. It's one of those things. So all elements have a oxidation number of 0. So your halogens, if they're diatomic gases, will be 0. Metals that are solid state are uncharged, have an oxidation number of 0. O2 will be 0. Anything that is in its elemental form will be 0. For ions, i.e. if it is in an ionic compound or it is a dissolved ion, then the charge is equal to the oxidation number. Okay, so for sodium +1, the oxidation number is +1. For chloride ions, Cl-, the oxidation number is going to be -1. And as we saw on the previous slide, for magnesium 2+, the oxidation number is going to be +2. So for an ion, it's always equal to its charge. Oxygen, when in compounds, is always given the value -2, except, because there is always an exception in chemistry, there is an exception where it is in peroxides, H2O2, or barium oxide. And in both these cases, it is -1. And you can kind of see that from the way that the formula is. H2O2, in order for this to be neutral, the hydrogen's going to be +1, the oxygens must be -1 each. Okay, and same with barium oxide, Ba2+. If I'm going to have 2 oxygens with it, then each oxygen must be bringing one minus with it. So there are exceptions there, just these two that you need to know. Hydrogen is basically treated like an acid. It's treated like a proton, so hydrogen is +1 in pretty much any of its compounds, unless it's attached to a very electropositive metal, and this is pretty much our group 1 metals. So where it forms a hydride, because hydrogen is taking the place of the negative ion here, it would be -1. But 9 times out of 10, it's going to be +1. When we have molecular ions and molecules, so things like SO4 2- or CO2, something like this, where we don't have clear ions and we don't have rules for all the elements, we need to use some simple algebra to calculate them. Okay, so we need to take the ones we do have a rule for and then work out the ones that we don't. So let's have a look at a couple of examples of those. So in this case, our example is to calculate the oxidation number of chromium in potassium dichromate. Okay, so hopefully you will realize that this is an ionic compound that is made up of K+, 2 lots of K+, and then we have Cr2O7 2-. Okay, so for a start, we know that the oxidation number of potassium is going to be +1. We have the oxidation number for oxygen. We have a rule for that, and each oxygen will have -2. The oxidation of chromium, however, this is not chromium solid, this is chromium in a compound, so we're going to have to calculate it. So we give it X. Okay, good old algebra, we're going to call it X. So now we can write an expression for this. Because the overall compound is neutral, then my expression is going to be equal to 0. Then I have 2 lots of my potassium. Then I have 2 lots of my chromium, which is unknown, and 7 lots of oxygen. Okay, so when I add that in, I'm going to have 7 lots of -2 +2. Okay, so this is going to be -14. This is going to be +2. So I'll end up with -12 plus 2x. When I rearrange, I'll get 2x plus 12 divide both sides by 2, and I'll get X is equal to 6. This is telling me that the oxidation number for chromium is plus 6. Okay, so let's have a look at a couple of other examples fairly quickly. Okay, so we're going to determine the oxidation number for each element, remembering that hydrogen is +1, oxygen is -2, okay, and then ions are equal to the charge. So let's have a look. In H2S, I have 2 lots of +1. I'm going to add up to 0 overall because this molecule is uncharged. Okay, so what I've got is +2 plus X is equal to 0. X is going to be equal to -2. So the oxidation state, or the oxidation number of sulfur, will be equal to -2. In the case of H2SO4, I have 2 lots of +1. I don't have a rule for sulfur, so that's going to be X, and then I have 4 lots of -2 is going to equal 0 because it's neutral overall. So this means that I'm going to have -8, not 80, -8 plus 2 plus X is equal to 0. So X is going to be equal to +6. So I have -6, so the oxidation number on sulfur will be +6. For KClO4, again, I know that potassium is going to be +1. In this case, I can't assume that the chlorine is going to be -1, because actually what we have here is K+, and then we have the chlorate anion, which is -1. So I need this ClO4 to add up to -1. Okay, so I've got 4 lots of -2. Okay, and I want to get to -1 in total, which means that the chlorine must equal +7. Because I'm going to go from -8, I need to add 7 to get to -1, and then this +1 here makes it neutral. So the oxidation number of chlorine is going to be +7. Okay, so essentially, if the oxidation number increases, we have oxidation. If the oxidation number decreases, we have reduction. Let's have a look at a couple of these quite quickly. When we go back to our combustion reaction where we combust solid carbon in the presence of oxygen gas to give us carbon dioxide, we can see that carbon is an element here, so it will be 0. Oxygen is an elemental, so it will be 0. Then here in CO2, we have 2 lots of -2, okay, because we've got 2 oxygens here, so this is going to be -4. Carbon must be equal to +4 to equal the neutral carbon dioxide molecule overall. So you tend to write the oxidation number above each atom, figure out what is happening to the oxidation. In this case, the oxidation number of carbon is increasing, so the carbon is being oxidized. The oxidation number of oxygen is decreasing, so the oxygen has been reduced. Okay, so oxygen will be the oxidant and carbon will be the reductant. So, another example. I want you to pause the video, have a go at this, and then come back and check your answer. Okay, so hopefully you came up with something similar to this, where you were able to work out that the oxidation number of sulfur was +4 in sulfur dioxide and went to +6 in the SO3, whereas nitrogen was +4 in the nitrogen dioxide and went to +2 in the nitrogen. This means because the oxidation number of the sulfur increased from 4 to 6, the SO2 was oxidized, making it the reductant, and then nitrogen went from +4 to +2, so the oxidation number decreased, so nitrogen dioxide, NO2, was reduced, making it the oxidant. Okay, that's it for oxidation numbers. Hopefully you've seen a few examples, and I recommend you try the questions in the booklet for a bunch of practice. You should now be able to calculate oxidation states, use the oxidation states to determine if a reaction is a redox reaction, remembering that essentially for it to be a redox reaction we have to have a change in oxidation state, and then be able to identify the species that has been reduced or oxidized using the oxidation numbers to justify your answer.